In 1998, two independent teams of astronomers set out to measure how fast the universe's expansion was slowing down. Not whether it was slowing down, how fast. The deceleration of the cosmic expansion was, at that point, considered settled physics. Gravity acts on everything. The mutual gravitational attraction of all the matter in the universe pulls inward, opposing the outward expansion that began at the Big Bang. The expansion must be decelerating. The only question was the rate. Both teams used the same method, Type 1a supernovae. These stellar explosions have a known intrinsic brightness. They are standard candles. By measuring how dim they appear at different distances, you can calculate how fast the universe was expanding at different points in its history. Compare expansion rates at different epochs and you get the deceleration. Both teams found that the distant supernovae were dimmer than expected. Not slightly dimmer. Dimmer in a way that required the opposite conclusion from the one they were looking for. The universe's expansion is not decelerating. It is accelerating. The galaxies are not slowing their recession from each other. They are speeding up. Something is pushing space itself outward at an increasing rate. Something that acts in opposition to gravity. Not locally, not in any region where matter is dense enough for gravity to dominate, but in the vast, empty spaces between galaxies where gravity is weak. Something that permeates all of space, exerts a repulsive effect on the expansion of the universe, and grows stronger, or at least remains constant, as the universe expands. This something constitutes approximately 68% of the total energy content of the universe. It has no agreed physical explanation. It has no representation in any confirmed theory of fundamental physics. The standard model of particle physics, the most precisely tested theoretical framework in the history of science, does not contain it. General relativity, which correctly predicts everything else about the large-scale structure of the universe, requires it as an additional term, but does not explain its origin or its value. We call it dark energy. The name is not a description. It is an acknowledgement that we do not know what it is. The Nobel Prize in Physics was awarded in 2011 to the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, for the discovery. The Nobel citation described the discovery as having shaken cosmology to its foundations. That is accurate. What it shook cosmology into was a picture of a universe in which the dominant component, the thing that constitutes 68% of everything, is completely unknown. This video goes through what dark energy is, what the data shows about its properties, what the leading theoretical explanations say and why none of them are satisfactory, and what the consequences are for the long-term future of the universe. There is a specific number in the fourth section of this video that represents what may be the worst theoretical prediction in the history of physics. A calculation that is correct in its methodology, uses only well-established physics, and produces an answer that is wrong by a factor of 10 to the power of 120. 10 to the power of 120. That number, and what it implies about our understanding of reality, is in the middle of this video. Everything else builds toward it. Before we continue, 68% of the universe is dark energy. 27% is dark matter. Ordinary matter, everything you have ever seen, touched, or measured, is approximately 5% of what exists. Drop a comment if you knew that before watching this. Most people who know the numbers do not know what they imply. The story of the discovery of dark energy is a story about two teams of astronomers who were competitors, who used the same method, who each expected to confirm the standard picture of a decelerating universe, and who both found the same impossible result. The Heisey Supernova Search Team, led by Brian Schmidt at Harvard, and the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, were the two groups. They were simultaneously analyzing samples of Type 1a supernovae at high redshift, supernovae in distant galaxies observed as they appeared billions of years ago. Type 1a supernovae are produced when a white dwarf in a binary system accretes mass from its companion until it reaches a critical mass, approximately 1.4 solar masses, called the Chandrasekhar limit, and undergoes a thermonuclear explosion. Because the explosion always occurs at the same critical mass, it always releases approximately the same amount of energy. The peak luminosity of a Type 1a supernova is therefore approximately the same everywhere in the universe. Not exactly the same. There are corrections to apply based on the shape of the light curve, the color, and other observational parameters. But after these corrections, Type 1a supernovae are standard candles, objects of known intrinsic brightness that can be used to measure distances across cosmological scales. The method is straightforward. Measure the apparent brightness of the supernova, apply the standard candle correction, calculate the distance. Compare the distance to the redshift, the velocity at which the supernova's host galaxy is receding. Do this for many supernovae at different distances, and you reconstruct the expansion history of the universe. Both teams assembled samples of high redshift supernovae, some at redshifts of 0.4 to 0.9, corresponding to distances of billions of light years and look-back times of billions of years. These distant supernovae show the universe as it was when the expansion rate was different from today. If the universe was decelerating, if gravity was slowing the expansion, then the distant supernovae should be slightly brighter than a constant expansion model would predict. Deceleration means the universe was expanding faster in the past than the redshift alone indicates, so the supernovae are slightly closer than expected, so they appear slightly brighter. Both teams found the opposite. The distant supernovae were slightly dimmer than a constant expansion model predicted. Not brighter, dimmer. Dimmer means further away than expected. Further away means the universe was expanding more slowly in the past than the redshift alone indicates. Slower expansion in the past and faster expansion today means the expansion is accelerating. Both teams spent months checking their results, looking for systematic errors, considering alternative explanations. Dust in the intervening space could make distant supernovae appear dimmer. Evolution in the properties of Type 1a supernovae at high redshift could bias the results. Gravitational lensing could affect the apparent brightness. Every alternative was analyzed. None of them adequately explained the observations. The results were published simultaneously in 1998. Rees and colleagues in the Astronomical Journal in February, Perlmutter and colleagues in the Astrophysical Journal in June. Both papers reported the same conclusion: the expansion is accelerating. The response in the cosmology community was not immediate celebration. It was disbelief, followed by intense scrutiny, followed by the gradual accumulation of independent evidence from completely different observational methods. The cosmic microwave background, the large-scale structure of the universe, baryon acoustic oscillations, all of which converged on the same conclusion. The expansion is accelerating. Something is causing it. We do not know what. The 1998 Rees et al. Paper in the Astronomical Journal and the 1999 Perlmutter et al. Paper in the Astrophysical Journal used samples of 16 and 42 high redshift Type 1a supernovae, respectively. Both papers reported evidence for a positive cosmological constant, dark energy, at statistical significances that would not, by modern standards, be considered definitive. The evidence became overwhelming only as larger supernova samples were assembled and independent lines of evidence converged. The Nobel Prize was awarded in 2011, after 13 years of accumulating confirmation. The cosmological constant, the mathematical term in Einstein's field equations that represents dark energy, has a history that predates the 1998 discovery by 83 years. Einstein introduced the cosmological constant in 1917 when he was applying general relativity to the universe as a whole. His equations, without modification, predicted a universe that was either expanding or contracting, not static. The prevailing assumption at the time was that the universe was eternal and unchanging. Einstein added the cosmological constant as a repulsive term that exactly balanced gravity, producing a static universe. When Hubble's 1929 observations confirmed that the universe was expanding, Einstein abandoned the cosmological constant and reportedly described it as the biggest blunder of his career. In 1998, it came back. Not as Einstein had introduced it, not as a device to produce a static universe, but as a measured physical quantity with a specific numerical value. A value that could be constrained by observation. A value that is positive, meaning the expansion is accelerating, and small, meaning the effect is observable only on cosmological scales where gravity between distant structures is negligible. Einstein's blunder turned out to be real. The value he chose was wrong. But the concept, a term in the field equations representing energy intrinsic to space itself, is what the data requires. The name dark energy encompasses three distinct physical possibilities. They are not interchangeable. They have different implications for the future of the universe, different relationships to known physics, and different levels of theoretical motivation. The first possibility is the cosmological constant. In this interpretation, dark energy is not a substance or a field. It is a property of space itself, the energy density of the vacuum, uniform everywhere, constant in time. Empty space has energy. The energy of empty space causes space to expand. As the universe expands, more empty space is created, which contains more vacuum energy, which causes more expansion. The process accelerates. The cosmological constant fits all current observations. It is consistent with every measurement of dark energy's properties that has been made. It is the simplest explanation, the one that requires adding the least new physics to the existing framework. The problem with the cosmological constant is its value. Quantum field theory, the framework that describes all known particles and forces at the quantum level, predicts that the vacuum should have energy. This is not a controversial prediction. It is a consequence of quantum mechanics. The Heisenberg uncertainty principle requires that even the lowest energy state of a quantum field has a non-zero energy, called the zero-point energy. The vacuum is filled with quantum fluctuations, virtual particles continuously appearing and annihilating, and these fluctuations contribute to the vacuum energy. The problem is how much vacuum energy they contribute. The naive calculation, adding up the contributions from all known quantum fields up to the energy scale at which we expect quantum field theory to break down, the Planck scale, gives a vacuum energy density of approximately 10 to the power of 93 grams per cubic centimeter. The observed value of dark energy, the value required to explain the observed acceleration of the expansion, is approximately 10 to the power of negative 27 grams per cubic centimeter. The theoretical prediction is wrong by a factor of 10 to the power of 120. Not 10, not 100, not a million, 10 to the power of 120. A 1 followed by 120 zeros. This is the number I mentioned in the introduction, the worst theoretical prediction in the history of physics. The discrepancy is so extreme that it cannot be a minor error in the calculation. Something is fundamentally wrong with the way quantum field theory handles vacuum energy, or something is fundamentally wrong with the way we are connecting quantum field theory to cosmology, or there is a cancellation mechanism that reduces the naive prediction by 120 orders of magnitude that we have not identified. No satisfactory explanation for this discrepancy, called the cosmological constant problem, exists. It has been recognized as one of the deepest unsolved problems in theoretical physics since the 1980s. It remains unsolved. The second possibility is quintessence. In this interpretation, dark energy is not a property of space, but a dynamic field, similar to the fields that describe known particles, but with the unusual property of having negative pressure that drives accelerated expansion. Unlike the cosmological constant, quintessence is not uniform in space and not constant in time. It evolves as the universe evolves. Quintessence models can, in principle, explain why the dark energy density today is comparable to the matter density, a coincidence that is difficult to understand in the cosmological constant picture, where the vacuum energy density is fixed, while the matter density has been decreasing for 13.8 billion years of cosmic expansion. The problem with quintessence is that there is no compelling physical motivation for the specific field required. Quintessence fields have been proposed, but they introduce new physics, new particles, new interactions that have not been observed and that require fine-tuning of their own. The third possibility is that general relativity itself is wrong, that gravity behaves differently on cosmological scales from how Einstein described it, and that the apparent acceleration is an artifact of applying the wrong theory to the large-scale structure of the universe. Modified gravity theories. Theories that extend or replace general relativity with a framework that behaves differently at large scales can, in some cases, produce apparent acceleration without requiring a dark energy component. But all such theories must reproduce the extraordinarily precise predictions of general relativity in the regimes where it has been tested: the solar system, binary pulsar systems, gravitational wave propagation. Most modified gravity theories have been significantly constrained by GW 170817, which confirm that gravitational waves travel at the speed of light to 1 part in 10 to the 15th, a result that eliminates most modifications to general relativity. The three possibilities remain viable in the sense that none has been definitively ruled out. None has been confirmed. The cosmological constant problem was first clearly articulated by Steven Weinberg in a 1989 Reviews of Modern Physics paper titled The Cosmological Constant Problem. Weinberg noted that the discrepancy between the theoretical prediction and the observed value was at least 120 orders of magnitude, and argued that the only known mechanism that could reduce the vacuum energy to the observed level was a mysterious cancellation of unknown origin. The paper remains one of the most cited in theoretical physics, and defined the problem as a central challenge for any theory attempting to unify quantum mechanics and general relativity. For 26 years after the 1998 discovery, the data was consistent with the simplest interpretation: a cosmological constant, dark energy with a fixed density, unchanging in time. In April 2024, that picture became less certain. The Dark Energy Spectroscopic Instrument, DESI, is a spectrograph mounted on the 4-meter Nicholas U. Mayle telescope at Kitt Peak National Observatory in Arizona. It is designed to measure the redshifts of tens of millions of galaxies and quasars across the history of the universe, mapping the large-scale structure of the cosmos in 3 dimensions and using baryon acoustic oscillations, characteristic patterns in the distribution of galaxies imprinted by sound waves in the early universe, as a standard ruler to measure the expansion history. DESI released its first-year results in April 2024. The results were consistent with a cosmological constant in most respects, but in one specific measurement, the equation of state of dark energy, the parameter W that describes the ratio of dark energy's pressure to its energy density, the DESI data showed a hint of deviation from the cosmological constant value. For a cosmological constant, W equals -1. Exactly. Always. For all time. DESI's first-year data suggested a value of W that may be changing over time, a dark energy equation of state that was different in the past from what it is today. The statistical significance of this deviation was approximately 2.5 to 3.9 sigma, depending on the specific dataset combination, below the 5 sigma threshold conventionally required for a confirmed discovery, but sufficient to be taken seriously. If dark energy's equation of state is changing, if W is not -1, but a function of time, then dark energy is not a cosmological constant. It is something dynamic, something that evolves, something more like quintessence than like vacuum energy. The DESI result is preliminary. It may not survive the accumulation of additional data. Statistical fluctuations can produce apparent signals at 2.5 to 3.9 sigma significance that disappear with larger samples. The history of cosmology is full of 3 sigma results that turned out to be noise. But it may also be real. And if it is real, it changes the theoretical landscape significantly. A time-varying dark energy equation of state cannot be a cosmological constant. A cosmological constant has W equal to -1 by definition, unchanging, eternal, a property of space-time itself. If DESI's hint is confirmed by its full 5-year dataset, which will be approximately 5 times larger than the first-year sample, it would rule out the cosmological constant as the explanation for dark energy. It would not tell us what dark energy is, but it would tell us what it is not. And eliminating the simplest explanation, the cosmological constant, would leave the theoretical landscape of dark energy candidates in a state of significant uncertainty. The next simplest explanations are quintessence models with specific field potentials that produce W slightly different from -1. But there are many such models, and they are not strongly constrained by current data. DESI's full 5-year dataset is expected in approximately 2026. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is conducting a complementary survey that will provide independent constraints on the dark energy equation of state from weak gravitational lensing and galaxy clustering. The Vera Rubin Observatory's Legacy Survey of Space and Time, beginning operations in 2024, will add another independent measurement. The next 5 years will either confirm the cosmological constant or reveal that dark energy is dynamic. The answer will determine which class of theoretical explanations is viable and which can be ruled out. We do not yet know which outcome to expect. The DESI first-year baryon acoustic oscillation results were published in a series of papers in April 2024, covering the methodology, the galaxy catalogs, and the cosmological parameter constraints. The hint of a time-varying dark energy equation of state emerged primarily from the combination of DESI data with external datasets, including CMB measurements from Planck and Type 1a supernova data from the Dark Energy Survey and Union 3 compilations. The DESI collaboration noted that the result was preliminary and that the statistical significance varied depending on which external datasets were included in the combination. There is a specific feature of the DESI result that makes it more significant than the statistical level alone might suggest. The hint of a time-varying dark energy equation of state in DESI's data is consistent with a dark energy that was less repulsive in the past, that had a less negative value of W at high redshift, and has become more repulsive over time. This behavior is described by a parameterization called W0W-ACDM, where W0 is the current equation of state and WA describes its rate of change. If this parameterization is correct, dark energy is not merely a fixed property of space. It is a dynamic entity that has been evolving over cosmic time, becoming increasingly dominant as the universe has expanded and matter has diluted. This picture, dynamic dark energy becoming more important over time, provides a possible explanation for what is called the coincidence problem. Why is the dark energy density today comparable to the matter density? In a cosmological constant model, this requires the vacuum energy to have a specific value that happens to produce rough equality between dark energy and matter at the current epoch, despite the two components scaling differently with the expansion of the universe. In a dynamic dark energy model, the evolution of the dark energy equation of state can, in principle, produce a tracking behavior in which dark energy density follows the matter density for much of cosmic history, before eventually coming to dominate, naturally explaining why the two densities are comparable today without requiring fine-tuning. Whether this is what the DESI data is showing, or whether it is a statistical fluctuation, is the central question in observational cosmology right now. Stop here. The DESI data suggests dark energy may be changing over time. If dark energy is dynamic, if it is not a cosmological constant but something that evolves, it opens the possibility that it could eventually change enough to alter the fate of the universe. The heat death scenario we described in an earlier video assumes a cosmological constant. If dark energy is dynamic, the ending might be different. Which ending do you think is more likely? Heat death or something we have not yet predicted? Drop your answer below. Let's go back to the number, 10 to the power of 120. This is not a number that appears in the context of dark energy and then disappears. It is a number that sits at the center of what physicists call the cosmological constant problem, and it is worth understanding exactly what this number means and why it is so disturbing. Quantum field theory is the framework that describes all known particles and forces at the fundamental level. It has been tested to extraordinary precision. The anomalous magnetic moment of the electron, predicted by quantum electrodynamics and measured experimentally, agreed to better than 1 part in a trillion. Quantum field theory is the most precisely tested theory in the history of science. Quantum field theory also predicts that the vacuum, empty space, has energy. This is not a peripheral result. It is a fundamental consequence of the uncertainty principle applied to quantum fields. A quantum field cannot be exactly zero everywhere. The uncertainty principle forbids it. Instead, it fluctuates. These fluctuations have energy. That energy contributes to the energy density of the vacuum. Calculating the vacuum energy density requires integrating the zero-point energy contributions of all quantum fields up to some cutoff energy, the energy scale above which the theory is expected to break down and new physics takes over. The most natural cutoff is the Planck energy, the scale at which quantum gravitational effects become important, approximately 10 to the 19th gigaelectron volts. With this cutoff, the predicted vacuum energy density is approximately 10 to the 93rd grams per cubic centimeter. The observed dark energy density, the value that explains the measured acceleration of cosmic expansion, is approximately 10 to the negative 27th grams per cubic centimeter. The ratio is approximately 10 to the 120th. This is not a rounding error. This is not a factor that can be absorbed by a better calculation or a more careful treatment of the physics. This is a discrepancy of 120 orders of magnitude between a theoretical prediction made using the most precisely tested framework in physics and a measured physical quantity. For context, the ratio of the mass of the observable universe to the mass of a single proton is approximately 10 to the 81st. The number of atoms in the observable universe is approximately 10 to the 78th. The ratio of the age of the universe in seconds to the Planck time is approximately 10 to the 61st. The cosmological constant discrepancy is larger than any of these numbers. It is the largest discrepancy between theory and observation in the history of science. The standard response to this discrepancy, the response that has been operative in theoretical physics for 40 years, is that there must be a cancellation. The bare vacuum energy, the contribution from quantum fluctuations, must be cancelled by some other term in the theory to within 120 orders of magnitude, leaving a tiny residual that is the observed dark energy density, a cancellation to 120 decimal places. This level of cancellation is called fine-tuning, and fine-tuning at this level is considered, by most physicists, to be a sign that something is fundamentally wrong with the theoretical picture, that the calculation is set up incorrectly, or that the theory is missing something essential, or that the cancellation is not a coincidence, but is enforced by a symmetry or mechanism that has not yet been identified. Supersymmetry was proposed as a mechanism that could cancel the vacuum energy contributions from bosons and fermions, which have opposite signs. If every fermion has a supersymmetric partner boson with exactly the same mass, the cancellation would be exact. But supersymmetry is broken. The partner particles, if they exist, must have different masses from their standard model counterparts. And a broken supersymmetry cancels the vacuum energy only partially, leaving a residual that is still many orders of magnitude too large. The Large Hadron Collider searched for supersymmetric particles at the energy scales where they were expected to be found if they were solving the hierarchy problem. It found nothing. The energy scale at which supersymmetry must be broken, if it exists at all, is now known to be higher than initially expected, making the cancellation problem more severe rather than less. The cosmological constant problem has not been solved. It has not been significantly reduced. The discrepancy remains 120 orders of magnitude after 40 years of theoretical effort. This is the honest state of the field. The cosmological constant problem is sometimes described as the worst fine-tuning problem in physics. A related but distinct fine-tuning problem, the coincidence problem, asks why the dark energy density and matter density are comparable today, despite scaling differently with cosmic expansion. Steven Weinberg's 1987 anthropic prediction that the cosmological constant must be small enough to allow the formation of galaxies, since observers can only exist in a universe where structure has formed, was cited as a possible explanation before the 1998 discovery, and was remarkably close to the observed value. The anthropic prediction does not explain the cosmological constant problem. It merely constrains the range of values consistent with observers existing. The nature of dark energy, whether it is a cosmological constant, a dynamic field, or something else entirely, determines the ultimate fate of the universe. We covered the heat death scenario in an earlier video. The heat death assumes a cosmological constant, dark energy with a fixed density that continues to drive accelerated expansion indefinitely. Under this assumption, the universe expands forever. Galaxies beyond the local group recede beyond the cosmological event horizon and become permanently inaccessible. Stars exhaust their fuel and die. Black holes evaporate through Hawking radiation over incomprehensible timescales. The universe approaches a state of maximum entropy, thermodynamic equilibrium, in which no further work can be done. This is the heat death. It is the fate of the universe if dark energy is a cosmological constant. If dark energy is quintessence, a dynamic field with an equation of state that changes over time, the fate depends on how the field evolves. Some quintessence models produce an equation of state that approaches -1 from above over time, dark energy becoming more like a cosmological constant as the universe ages, producing heat death as the asymptotic outcome. Other quintessence models produce an equation of state that evolves toward values more negative than -1. This regime, W less than -1, is called phantom dark energy. Phantom dark energy has properties that violate the null energy condition, a fundamental constraint in general relativity that is satisfied by all known forms of matter and energy. A universe dominated by phantom dark energy does not approach heat death. It approaches something far more violent, the Big Rip. In a Big Rip scenario, analyzed in detail by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg in a 2003 Physical Review Letters paper, the dark energy density increases over time as the universe expands, rather than remaining constant. The increasing dark energy density drives increasingly rapid expansion. As the expansion rate increases, the dark energy density increases further. The feedback is runaway. The The consequence is that the expansion rate eventually exceeds the gravitational binding force holding together every structure in the universe, in sequence from the largest to the smallest. Galaxy clusters are the first to be torn apart, as the expansion rate exceeds the gravitational binding of the cluster. Then individual galaxies, then stellar systems, then planets. Then the planets themselves are torn apart as the expansion rate exceeds the electromagnetic and gravitational forces holding matter together. In the final moments, the expansion rate exceeds the strong nuclear force, the force that holds protons and neutrons together inside atomic nuclei. Nuclei are torn apart. Then individual nucleons. Then, in the final fraction of a second, the expansion rate exceeds the forces holding quarks together inside nucleons. The universe ends not in cold darkness, but in a catastrophic expansion that tears apart every structure at every scale simultaneously, down to the level of elementary particles. The time remaining to the Big Rip, if the DESI hint of phantom dark energy is confirmed, is approximately 10 to 20 billion years from now, not in the far future, on a timescale comparable to the current age of the universe. The Big Rip is not the consensus prediction for the fate of the universe. The cosmological constant, heat death, remains the most observationally supported scenario. But the DESI hint, if confirmed, suggests that dark energy may be phantom, and if it is phantom, the Big Rip timeline is not remote. The data is not yet definitive. The result from DESI's first year may be a statistical fluctuation. The full dataset will clarify. But the possibility that the universe ends in 10 to 20 billion years, in a catastrophic expansion that tears apart atoms, rather than in the cold, slow heat death over quadrillions of years, is currently consistent with the observations. The Big Rip scenario was first analyzed in a 2003 Physical Review Letters paper by Caldwell, Kamienowski, and Weinberg, titled Phantom Energy, Dark Energy with W less than -1 and the Big Rip. The paper calculated that for a phantom dark energy equation of state of W equals -1.5, the Big Rip would occur approximately 22 billion years from now. For W equals -1.01, the timescale extends to approximately 1.5 trillion years. The precise timing depends sensitively on the equation of state value. The DESI first-year results are consistent with a range of W0 and WA values that includes both phantom and non-phantom dark energy. The cosmological constant problem, the 120 order of magnitude discrepancy between the predicted and observed vacuum energy, has one proposed resolution that is qualitatively different from all others. It does not solve the problem by finding the cancellation mechanism. It sidesteps the problem by asking a different question. Why does the cosmological constant have the value it has? In 1987, before the observational discovery of dark energy, Steven Weinberg published a paper in Physical Review Letters arguing that the cosmological constant could not be too large. If the vacuum energy were much larger than it is, the universe would have expanded too rapidly for galaxies to form. No galaxies means no stars. No stars means no heavy elements. No heavy elements means no planets. No planets means no observers. Weinberg argued that observers can only exist in universes where the cosmological constant is small enough to allow structure formation. If the cosmological constant varies across a large ensemble of universes, the multiverse, then observers will only find themselves in the subset of universes where the constant is compatible with their existence. The observed value is not the only possible value. It is the value that observers can observe. This is the anthropic argument. It does not explain why the cosmological constant has its value in any fundamental sense. It explains why observers in a universe with that value would expect to observe it. Weinberg's 1987 prediction made before the observational discovery, suggested a cosmological constant approximately 100 to 1,000 times smaller than what quantum field theory predicted. In 1998, the observational value was found to be approximately in this range. The anthropic prediction was not precise, but it was in the right order of magnitude when quantum field theory's prediction was off by 120 orders. This has been taken by some physicists as evidence that the multiverse is real, that we live in one of an enormous number of universes with different physical constants, and that we find ourselves in a universe with a small cosmological constant because that is the only kind of universe that can contain observers. The multiverse interpretation of the cosmological constant is deeply controversial. It cannot be tested directly. By definition, other universes are not accessible to observation. It may not be falsifiable in any conventional scientific sense. Some physicists consider it a legitimate scientific framework because it makes statistical predictions about which values of physical constants should be most common among observers. Others consider it a philosophical position that goes beyond what science can address. The debate is ongoing. It has been ongoing for decades. It will not be resolved by the DESI dataset. What DESI may resolve is the simpler question. Is dark energy a cosmological constant or something else? If it is something else, if the equation of state is changing, then the cosmological constant is not the explanation for dark energy. The anthropic argument in its simplest form does not apply, and the theoretical landscape becomes significantly more open. A more open theoretical landscape means more possibilities. It does not mean answers. Weinberg's 1987 anthropic prediction of the cosmological constant appeared in Physical Review Letters under the title Anthropic Bound on the Cosmological Constant. Weinberg used the requirement that the cosmological constant must be small enough for galaxies to form, since observers require galaxies for their existence, to place an upper bound on the vacuum energy density. The bound was approximately 500 times the current matter density, which is within an order of magnitude of the observed value. The prediction was published 11 years before the observational discovery of dark energy. In 1998, two teams of astronomers set out to measure how fast the universe's expansion was slowing down. They found that it was not slowing down. The cause of the acceleration constitutes 68% of the total energy content of the universe. It has no agreed physical explanation. The best theoretical prediction for its value is wrong by a factor of 10 to the power of 120. The most recent large-scale observational survey suggests it may be changing over time, which would rule out the simplest explanation, but the evidence is not yet definitive. The fate of the universe depends on which explanation is correct. A cosmological constant produces a slow heat death over incomprehensible timescales. A phantom dark energy field produces a big rip that tears apart atoms in 10 to 20 billion years. We do not know which it is. The Standard Model, which describes 5% of the universe, is the most precisely tested theory in the history of science. Dark energy, which constitutes 68% of the universe, has no description in any confirmed theory. The universe is, in the most literal sense, mostly unknown. The data exists. The observations are real. The acceleration is measured. The discrepancy with theory is 120 orders of magnitude. These are not gaps at the edge of knowledge. They are gaps at the center. And the center is where 68% of everything is. One question: if the DESI result is confirmed, if dark energy is dynamic, evolving, phantom, and the Big Rip scenario becomes the predicted fate of the universe in 10 to 20 billion years, rather than heat death in quadrillions, does that change anything for you personally? Does the timeline matter? Is there a meaningful difference between heat death in 10 to the 100th years and a Big Rip in 15 billion years from the perspective of anyone alive today? Drop your answer. I want to know where the threshold of caring about cosmic timescales actually is for people. Next video. The universe is flat. This is one of the strangest confirmed facts in all of physics, and it should not be. The probability of the universe having exactly flat geometry by chance is approximately 1 in 10 to the 60th. Something made it flat. That something is called inflation. And inflation has implications that most people who have heard of it have not fully followed to their conclusion. See you there.